In this video, we'll talk more about buffers by looking at a titration curve, talking about polyprotic acids, and looking at some acid-base practice problems. So this is what a typical titration curve would be like. So if we were thinking about our 50 milliliters of 0.1 molar acetic acid titrating with the 0.1 molar NaOH, and we plotted this at several different volumes of NaOH, we'd get a graph that looks something like this, going all the way from 0 to whenever we stopped. So there's some features of this graph that we'd like to point out. The first is this buffer region. So this is the buffer region where the pH change is going to be minimal. So as we're adding base here, the pH does not change very much in this direction. And that's because we have both the weak acid and its conjugate base present. This buffer region is going to be when the pH, right here, is within 1 of the pKa. So remember, for acetic acid, the pKa was 4.74. So what this means is that acetic acid would be a good buffer in the range from 3.74 to 5.74. So that's the range in which acetic acid can resist changes in pH. This also corresponds to what we were talking about before when the Henderson-Hasselbalch equation applies when A minus over AH is between 0.1 and 10. This is the same thing as saying that the pH is going to be equal to the pKa plus or minus 1. The next thing we'll see is near the equivalence point. So remember, when we added as much base as we had acid, we all of a sudden saw a jump up in the pH because we have now neutralized all the weak acid, and now this is just acting as if we're just adding straight up base present. So we'll see a steep increase, and the pH in the middle of there should be higher than a neutral value at the equivalence point. In practice, if we were trying to find the half equivalence point, which is, remember, where the pH is equal to the pKa, the easiest way to do this would be to do a slow titration, see the volume where it jumps up suddenly, so this is a really narrow band, take half of that, and now would find the half equivalence point, and whatever the pH was at that point, that would be our pKa as well. For a polyprotic acid, this titration curve is going to look a little bit different because we can have multiple protons that dissociate. So using phosphoric acid as an example, if we add a base to this, we'll lose one of the protons, but we still have 2 acidic protons left. So what you'd see is a flat region and sort of a first buffer region that corresponds to this first pKa. The subscript 1, so pKa 1, tells you that this is a polyprotic acid with multiple protons, and this is the pKa for losing the first proton. So once we reach the equivalence point, we'd see a steep jump again, and then as we added more base, we see that the OH minus is now going to neutralize a second proton in the reaction. So as we go up, we'd get another flatter region. This would be the second buffer region. And in the middle here, at the second half equivalence point, the pH is going to equal to the second pKa. So the second half equivalence point is going to happen after we've added 1 plus a half the amount of base as the original acid. When we get to the second equivalence point, we're going to see another steep jump as we've neutralized now all of the H2PO4. And then in this case of phosphoric acid, which has 3 different acidic protons, we will see the last buffer zone where we're losing the last proton. The middle of this range will be our pKa 3, and that would be the pKa related to losing that last proton. So if you see one of these titration curves with multiple flat spots, the number of flat regions tell you how many acidic protons they are. So in this case, this would be a diprotic acid or an acid with 2 acidic protons. Contrast that with here, where we have the 3 buffer regions for a triprotic acid with 3 acidic protons. Okay, so let's do a little bit of review for identifying buffer solutions. So which of the following of these solutions would be a buffer? And the answer for here is neither. So let's take a look at why we would get that. So remember, for these we want to identify the major species. So here this would be H+, Cl-, Na+, Cl-. So here all we have is a strong acid. These are all neither. We would still have water. This is just going to be an acidic solution, not a buffer solution. Here we have HF, OH minus, Na plus, and water. We know that the OH minus will react with the HF. But if you look at the amounts here, we can see that we actually have more base than we have acid. So if we did this reaction, the limiting reagent would be the weak acid. And the major species after this reaction would just be OH minus, F minus, and water. And these are all bases. So this would also be just a basic solution. Okay, let's look at another practice problem. So in this one, we have 40 milliliters of 1 molar hydrochloric acid mixed with 30 milliliters of barium hydroxide. Is this solution going to be acidic, basic, or neutral? A hint for this one is to watch out for the mole ratios for these species. And this one will be basic. So hydrochloric acid is HCl. Barium hydroxide is going to be BaOH2. And so even though this salt isn't that soluble when we're reacting it with HCl, we get this equation where we see we need twice as much HCl to neutralize the barium hydroxide because there's 2 of these OH minuses here in this equation. We still have the net ionic equation for an acid and a base, but in this case, this base comes with 2 OH minuses, so we need to neutralize both of them. So in this case, even though we have a lower volume, we still have more hydroxide ions, and this will be a basic solution. The last one we're going to look at is this question where we will try and work the Henderson-Hasselbalch equation through backwards. So here we have an equilibrium. We're given the pKa, and we're given that we have 250 milliliters of a 1.0 molar HClO solution. So at the beginning, this solution, since it's just the weak acid, is not a buffer solution. We want to make a solution that is a buffer and buffered at a pH of 7.2. And the question is, how much solid NaClO will we add to make this buffer? This is telling us to assume the volume of the added solid is negligible, so we don't have to worry about changing the volume or changing the concentrations. Okay, so let's look at how we would set this up. So since we're making a buffer, remember we can use the Henderson-Hasselbalch equation. So the pH is going to equal the pKa plus the log of A minus over AH. So if we plug in the numbers, we see that our pH that we want, 7.20, would be equal to the pKa, 7.46, plus the log of the A minus over the AH. So if we take the difference here, we get negative 0.26 is equal to the log A minus over AH. And if we take 10 to the both sides, we get 0.55 is equal to A minus over AH. And remember, we can do this as moles since the volumes would cancel out. So we get the moles of A minus is equal to 0.55 times the moles of our acid. And to find this value, we can use our volume and concentration. And that gives us that we need 0.14 moles of NaClO. The question was how many grams. So to finish this up, we'll take our 0.14 moles and multiply it by the molar mass to get that we need about 10 grams of the NaClO added to this original solution to make this buffer.